You can turn it in on the way out. Okay, so we are on the orbital approximation, mini electron atoms. So we're kind of changing gears now. Because, Ashley, we were working with hydrogenic atoms, which meant what? Okay, one electron. We went through this so many times. One electron, right? Okay. So now we're changing gears, talking about mini electrons. So we already solved the Schrödinger equation. So what they're going to do with these mini electron atoms is they're going to say, okay, here's our wave function. And look at, here's all your little electrons, R1, R2, R3, describing their position. And these are going to be our hydrogenic wave functions that we had before. Okay, so that's what they're going to do. So the individual hydrogenic orbitals that all the different little electrons lie in. That's how we're going to generate the wave function for a mini electron atom. And before, do you remember we talked about how electron configuration, you had like 2s2, 2p3, right? All these kind of things. That's how we used to describe electron configuration. What we're going to do for mini electron atoms is we're going to start using terms. And the book is introducing this now, and we don't really know what a term is, but it's going to be how we're going to describe the different states and the electronic configuration. We're going to use terms, okay? The Pauli exclusion principle only applies to fermions. What's an electron? Is an electron a fermion? Yeah, electron's a fermion. Photons are, starts with the B, bosons, yeah. So that's neither here nor there, but okay. What? Photons. Okay. So shielding. We have, what they're trying to say is that in NMR we talked about this. Remember how different protons had different chemical environments? Well, same thing here. Where's the nucleus in this thing, Pablo? In this diagram? Where's the nucleus? Yeah, that dot right in the center. Okay, so what they're trying to say is that the electrons within some radius r are shielded from the nucleus. And the electrons outside that radius have no effect. All they're trying to say is, what's the charge on the nucleus? What's it? Positive. What's the charge of an electron? Negative. So at that distance r, right, that's where this electron is supposed to be. Well, what's between it and the nucleus? More electrons. Because we're talking about mini electron atoms now. So there's electrons, all over. But the electrons that are between the nucleus, that are in between the electron we're interested in and the nucleus, they end up just shielding, right? It's repulsion is all it is, because what's the charge on electrons? Negative. So if you have nucleus, electrons, all at some distance r, another electron, it's just shielding. It's just repulsion. Which, if it's repulsion, that means that the electron out at a radius r isn't going to feel a full charge. Because there's some repulsion there.
Sorry, this may seem like a silly question, but we talk about our SP and the various orbitals. Is that like dumbbell shape or spherical shape? Does that make a difference?
Now, what solution? That's for what type of atom? That's solutions to the Schrödinger equation for what type of atom? Hydrogenic. How many electrons is that? One. You change the number of electrons, do you have a whole new wave function we have to use? You bet we do, right? But we're using those orbitals that you're referring to, S, P, D, 3D. We're using those solutions, those orbitals, right, to generate the wave function for a mini electron atom. So we're still using that, and it gives. You'll see later on how it gives answers. Okay. They talk about a closed shell, right? Where closed shell is pretty much just that the angular momentum is 0. The net angular momentum is 0. And usually we think of that as spin pairing, right? And that's what they're trying to illustrate in this diagram, okay? Where you have the, and what was this called? Where the angular momentum is actually precession. Yeah, it's actually rotates in a cone. Okay.
And it's an angular momentum, right?
Yep. So we have effective nuclear charge. Okay. So what's Z? What's Z, Richie? What did they call it? You've seen it before? What do we call it? The atomic number, right? Z is the atomic number. Nothing complicated. Z is the atomic number. So the effective nuclear charge that an electron feels, is it the full atomic number? Is it the full nuclear charge? Or is it a little bit less?
Less.
It's a little bit less because look at the equation. The effective nuclear charge is Z minus sigma. You're subtracting something, right? So you're not feeling the full charge. Okay. And why aren't you feeling the full charge? What do we call it? Shielding. Okay. So if you take a look at what these constants are, these shielding constants, they're tabulated. Okay. And it's just, why would the shielding constant get bigger?
More electrons.
Bigger out here.
There's more electrons in the radius.
There's more electrons in the radius. Exactly. Right? Because we're talking about much further out. Exactly. Very good. You're following.
Okay, so we're talking about the charge that the electron feels.
The effective nuclear charge.
I just
Okay.
wanted to make sure we're looking at it from the electron's point of view. Not
Yes, this is all from the electron's point of view.
These are that sigma zero on the table.
Yeah, and they're constants, right? They're constants.
That was
Okay. Pretty much fudge factors to get the right answers and what we're going to be coming up with. Okay. But it makes sense that you're subtracting something. And those numbers should be different for different orbitals because of, like Pablo said, I mean, look at the radius is going to be different for much larger for 2p comparison to 1s, for example. Okay, so there should be more electrons between the nucleus and that electron we're interested in. Okay. So another way to look at this idea of shielding is penetration. So instead of thinking about electrons, what are they doing? Repulsing or attracting one another?
Electrons are
Repulsing one another. So instead of thinking about shielding, which is electrons repulsing one another, let's think about how close that electron is to the nucleus, right? The closer it is, are we talking about potential energy or kinetic energy?
the closer to
Because the nucleus is what charge? Positive. Electrons, negative. The closer it gets, the stronger the attraction. Are we referring to potential energy? All right? And are we talking about negative energy or positive energy? Negative is the convention. So we're talking about this potential energy well, right? How the closer you are, right, the greater the potential energy. And all we're trying to illustrate, here's some diagrams. We have our solutions to the which atom? Hydrogen atom with the Schrödinger equation. Here's 1s, 2s, our 2p, our 3d. Okay. These are, now some lobes are dark, some are white, and that's just, the sign of the wave function. And there are some interesting things, some terms. Like, what do we call this space right here? Starts with an N. A node, right? Which one has more energy, the 1s or the 2s? Just by looking at it. What happens if a standing wave has more energy? It should have more what? Nodes, right? So do you see any nodes with 1s? No, there's a 2s has a node. Okay. So that's a cross section, right? Because if you're just looking at it from the outside, it would look just like the 1s, but probably bigger. Okay.
So the greater the nodes, the greater the potential energy.
The energy. All right. We're not talking the greater the energy of that orbital. When I refer to potential energy, we're referring to be something being stable. But now, when you say greater potential energy, the convention is a greater negative energy. It's more stable. It's way down here. So the greatest potential energy would be the 1s. Why? Because look how close it is to the nucleus. They're so attracted, exactly. So you got to be careful with the language. When we say greater energy, 2s is greater energy than 1s, right? We're talking about it's a higher energy level than this one. When we talk about potential energy, we're talking about a greater negative energy, that it's more stable, right? You're talking about ground state. The further down you get in the energy well. So 1s is much, much closer to the nucleus than 2s. And look at p's, things are just getting farther out. D's, things are getting even farther out. Because look at that. Look at the D especially, and the P. There's an angular node at the nucleus. Very different than over here. So that's where these plots are coming from. They're trying to say that, okay, that this idea of penetration instead of shielding can also explain why these orbitals are now different energies. With hydrogenic atoms, Ashley, was the 2s and the 2p the same energy? Go back. Go back in the notes. Get some nice plots of that stuff. Look at that. Here's n equals 2. So this is the 2s, the 2p. Are they degenerate? Yeah. Hydrogenic, how many electrons? 1. Many electrons, story totally changes. These orbitals are no longer degenerate. Because of what? You can pick one of two. 2s is no longer degenerate with 2p because of shielding or penetration.
So penetration would be electrons, protons, and
Yeah, and those some orbitals are just simply more closer to the nucleus than others. Okay. The building up principle. Oh, valence electron. We've heard of those, right? These are the outermost or innermost or what? Outermost. If you want to talk about bonding or reactivity, what electrons are you supposed to be referring to? The valence electrons, right? They would feel what? The strongest nuclear charge or the weakest? When you refer to effective nuclear charge, what would they feel? Weakest, right? And again, you can think of it two different ways. You can think of it because of shielding, or you can think of it in terms of penetration. Okay. That's all it really is, because that's what this is trying to say. This is all about distance. The farther out you go.
What does ZR stand for?
What's Z?
Yeah.
Z is atomic number. What's A naught? What's A naught? Bohr's radius. If you have a hydrogen atom, it's the most likely radius. Okay.
That's what A naught is?
Mm-hmm. It's the Bohr radius, remember? Way back in the beginning of this chapter.
So ZR is just atomic number?
Mm-hmm. And R is the
Radius?
R is the radius. Yep.
Or the distance between
Mm-hmm.
Because I guess in theory, each electron would have a different radius.
Mm-hmm. Yeah, each electron has to have its own set of quantum numbers, its own orbital, right? So yeah, and now they're not degenerate anymore. before they were hydrogenic. The building up principle. If you have Z less than 10, then this, what we used to work over here, no problem really for getting electron configurations of what orbital fills up first, second, third. So, but we're just going to use this. And we spent a lot of time on our concept preview using this. So I'm not going to go over that again. Hund's rule, right? Which one is a lower energy? Which one? Ricky, which one?
I think it's the one on top.
Exactly. It's the one on top.
The one on the bottom looks all screwy and
It's the one on top. Okay.
Probably more energy easier.
Okay. We have, yeah?
Oh, I see. So that's an electron configuration, right?
Yeah. And we're going to be needing to do this correctly to write the terms.
What does that say, lower what?
Energy. Okay, first ionization energy. Let's see here. So here's the first ionization energy, the second ionization energy. What is ionization energy? Richie, what's ionization energy? What is that?
Well, isn't the energy needed to drive off or add an electron to something or ionize it?
Which one? Drive off or add one?
Drive off.
Drive off. Add on. Ashley, which one is it? Want to ionize something. Yeah, you're creating an ion. You have to create an ion. So, but it's a cation. So energy to remove an electron. Okay. What's the word for energy to add an electron? I think we only used this word once, and it was in general chemistry.
What was the question?
What do they call the energy to add an electron? Electron affinity. Yeah, we never use that. Okay. Anyway, so we have a column for first ionization energy and second ionization energy. Pablo, which one's always higher?
First?
Look at sodium, for example. Look at any one of them.
Second?
Is the second always higher, Richie?
Yeah.
Yeah. Why is that, Bradley?
The question is, why is the first one always higher, or the second one always higher?
Yeah.
Oh, I imagine it's because it would have a smaller radius, so it'd have a greater affinity.
Okay, okay. So you removed an electron. Has a smaller radius. That's a smart. You're on track. Except it's wrong. But it's right, but it's not the major reason. It's kind of like the same argument as to why does the Earth have seasons. It's not because of being closer or farther away from the sun. It's the tilt, right? So it might have a little effect, but it's not the major component. The 90%. No. If you ionize something, what are you left with? A charge. What is it, positive or negative?
Positive. Because you drove off.
You drove off an electron, so it has to be positive. Okay, that's your first ionization energy. It took energy to do that. Your second ionization energy, you have to remove a second electron. Now you're not removing this electron from something neutral. You're removing it from something that is positive. What's the charge on an electron? Negative. That's going to take a lot of work. So second ionization energy is always higher than first ionization energy, simply because of that. You're removing an electron from something that is positive.
So you're saying closest system doesn't cost.
Okay. So I don't remember Spartan well enough to remember this, but you had some choices in the calculations. You probably blew over it so fast, but you had SCF, self-consistent field orbitals. And what they're doing is, what that software is doing is it's just messing around with the orbitals. And it's just picking different orbitals to try to give the right answers. Because it knows what the ionization energies are, for example, and just from experimental values. So it just messes around with these wave functions to get the best ionization energy. And once it gets the closest answer, then it can use those wave functions, that wave function, with those hydrogenic orbitals to get vibrational energies, to get molecular shape, to get dipoles, to get polarity. It can, right? So that's one game that a computer can like Spartan, can play. Quantum defects. Okay. So we had our energy. So things aren't really changing too much. I mean, Rydberg state is when this equation works. It's not always going to work, right? But when you have n squared in the denominator, then it's called a Rydberg state. But if you, all right, so empirical means what?
Determined by
Experiment. Experiment. You got to introduce a little fudge factor to get the right answers. Okay. That delta. And delta is called the what is it called? The quantum defect. Okay. And pick your choice. I mean, either shielding or penetration. That's the argument as to why we need a fudge factor in there. Okay. So we are now talking about non-hydrogenic atoms, right? Mini electron. So we write the wave functions by just kind of doing what we did before, but we have to write a bunch of them. One hydrogenic wave function for each single electron. So it's in its own orbital. Okay. Hmm?
Is it gonna be like many size stars, or has
Oh, it would be so ugly. I bet you we're not going to be writing wave functions. Let's find out. I don't think it's going to be that. I mean, remember how complicated it was just to write one wave function for one electron. Okay. So I think this is computer stuff if you want to do that kind of thing. So let's see what the homework.
here's a board?
Let's see what the homework wants here.
It's like question 5, but it's like
Like question 5, but like 20 more pages. I'm pretty sure it takes up 2 pages to write it.
Okay, so here's the first one. Ultraviolet radiation of wavelength 58.4 nanometers from a helium lamp. Ashley, what's the easy way, right off, oh, where'd she just go? Ashley. Okay, Richie, fine. I guess my brain is just used to working these problems out. When I see 58.4 nanometers, I don't read the word nanometers. In my head, I see that number as looking like what? 58.4 times 10 to the negative 9, right? And when you start seeing stuff like this way, you're kind of preparing yourself so the question is less ambiguous, right? These little tricks like that. Anyway, the ultraviolet radiation, 58.4 times 10 to the negative 9 meters, from a helium lamp is directed to a sample of xenon. Electrons are ejected with a speed of 1.79 times 10 to the 6 meters per second. Calculate the ionization energy of xenon. How do you do this? And what does this have to do with anything? the heck?
So do you do this
What's
one?
the trick
like,
to this?
Do you do like Planck's constant times speed of light over that wavelength in meters minus the kinetic energy? Or no?
Okay, now we're getting a few thoughts here. Like Ricardo was saying hc over lambda, right? Now what is that? That's the energy of the what? Of the photon. Okay. What's the total energy that you have to work with here? What's the total energy? Because you also mentioned the word kinetic energy of the electron, and that's good because that's going to be the speed of the electron. That'd be little v, right?
Yeah, probably did that one wrong.
But what's the total energy you have to work with? What has to happen? This photon's coming in, right? Blasts xenon, and what happens? Loses an electron, right? Now, did it take energy to suck that electron out? Yeah. In fact, isn't that what we're solving for? Yeah. Okay. So the energy before has to equal the energy after. So what's the energy before they have to work with?
HC over lambda.
The hc over lambda. So that hc over lambda is the energy you have to work with. That's the energy before. So that has to equal what?
1/2 mv squared.
What happened afterwards? What's 1/2 mv squared?
Well, 1/2 times the mass of the electron.
Yeah, what does that represent?
Yeah,
Kinetic energy of what?
of the electron.
Of the electron. Okay, so that's part of the after. Well, what's the rest of it? Before you even got that, what had to happen? Before you even got that kinetic energy of the electron, before that electron's kicked out, what had to happen? The electron's in xenon. It had to get ionized, had to get kicked out. So what would you write on the other side? This energy of this photon has to equal.
Equal the kinetic energy plus ionization.
There you go. Can you see that? Has to equal the kinetic energy of the electron plus. What did you say? Oh, what do we want to call it?
Plus the ionization.
I don't know, big IE or something. I don't know, whatever you want to call it. And what's the equation for kinetic energy? Richie? Ricardo said it. 1/2 mv squared. And standard metric units for everything, and you'll have it. Right? Okay. How about, that makes sense? Can we go on?
Yeah.
Locate the radial nodes in the 3p orbital of a hydrogen atom. I want you to think about this for a little bit. We mentioned how to do this in the notes.
That last one we just did was 13.1b, right?
Yeah.
Yeah.
Radio.
We haven't done these problems.
This is
yet,
stuff we
right?
have to look at the table.
We gave a starting point in our notes.
I know how to do this. You have to look at the table. And then your 3 is going to be your n. Or your, also you're going to calculate your n and l.
I have problems with this kind of problem.
Oh, let me see if I can find where we talked about this.
So you need to look at your table textbook.
Yeah. Go back. It's on day 1. Day 1 in our notes. I'm just thinking of, this is what I'm trying to get you to do. When I said normalize something, we wrote an initial expression. Okay. What's the initial expression you write when you want to locate radial nodes?
Do we have to look at that table on 3?
I was pretty sure it was the
Oh,
table.
the general one? Is that the side?
Where's the expression?
IR?
It was on the day 1 notes.
The one for
Right? Radial nodes. Radial wave function. Radial nodes. What does that mean? Because that, we didn't only talk about, I'll see if I can get you bang your memory here. We talked about how to find radial nodes. We talked about how to find radial extrema. We talked about how to find the most probable radius. So there's 3 starting points that you got to know. This one, they want to know, hey, where are the radial nodes? What was the expression that you wrote? Your big R had to equal what? 0. Right? Your big R had to be 0. Okay? And we're talking about 3p, so I don't know, you can write a little 3p down there. Because you have to write, and you look these guys up. Okay?
Radial.
What do we call it? The radial wave function, right? Because we said that, you remember we said that our wave functions were like some, right? Remember this? So this is the part we're interested in. This is going back to day 1. Okay. So find, I think I scanned that for next year. Yeah, here it is. Okay. So, dang. I'm going to delete this from this table. Because you guys had a lot of trouble doing this, that's why.
Yeah.
Right? So if it's 3p, you got to figure out, oh yeah, that's n is 3, little l is what? 1. Right? We had a lot of trouble doing that.
It's too complicated.
So what are we going to set equal to 0? This whole big thing.
Yeah.
Right?
You have to what? Oh, you're gonna copy all that.
So that whole set this whole big thing equal to 0, but it looks uglier than it really is. Because you can get rid of so much stuff. It equals 0.
Because
Right?
the only constant in there is R, right?
Yeah, the R is what you're solving for.
So
Okay.
you don't have to do anything weird like integrate or anything. You just set that to 0,
Set that to 0.
and then do what?
And that's your answers.
R.
Those are your
You
answers.
said we gave you that.
Okay.
Wait, you set that equals 0 and you solve for R.
Mm-hmm.
Yep. Yes, sir.
Where's the R?
Yeah, that's what I was looking for. Is it in the row?
Your row, yeah.
Oh,
Because you push your row out with them, it tells you.
And rho is the P,
Yes.
not to be confused with linear momentum.
Exactly.
The heck? What is that? 13.
Okay.
Yes.
We did one of those before, I think. Maybe. Okay. So you got a starting point on that one. We can come back and finish these. I just wanted to get a starting point on these guys. So you have a starting point, right? How about 13.4b?
You like that express as wave function.
Hmm?
That's the wave function. So how are we saying what?
Okay. This is supposed to be a subscript, right?
Where?
This little 0 written here. It's e the negative
Yeah,
r
A,
over
naught.
2 a naught.
Yeah.
Okay.
Easier,
Okay. So
It's a triple integral. Yeah.
they want normalization. So what's the very first expression you should write?
Side star side.
Equals what?
1.
1. Right? In fact, you should write what down here?
D tau.
D tau, because it's the general expression. This is your starting point. Just like your radial wave function equals 0 is your starting point for radial nodes. So when you think of radial nodes, boom, I'm just thinking, okay, the radial wave function has to be 0. And this only makes sense if I know what these things are called. Right? If you look at this wave function, if you don't recognize this as a wave function, you're screwed. If you don't know that R represents the radial wave function, you're screwed. If you don't know Y is spherical harmonics, you're screwed. So you need to know what it's just like PV equals nRT. If you don't know what these different little symbols represent, you can't do this stuff, right? So you got to know what these different symbols represent.
I see.
Okay. Good deal.
Pablo knows there are the.
Yeah.
That's what I'm saying.
Okay. Now, why do you think this hint was given?
Because it's triple integral.
Because triple integral. Because if I was going to do this problem, if I was given this integral, if I was given this wave function, my d tau probably would have just been
Dx.
dr, right? That's why I gave this hint, because I personally would have done just dr. That's why the hint is in there, because it's not. You have to, it's three-dimensional.
So are we assuming?
Fancy integral.
Are we assuming? More than one electrons are automatically triple integrals. It's considered for two atoms.
I think I don't think, Pablo, we've come across a problem that had just dr. I think whenever you saw an r, it was a triple integral.
Yeah, you're right.
I really think it is. So it's just automatic. How-
For 13.4b,
Mhm.
it's two atoms, right? Or two electrons. So we're not dealing with one. So does that mean we write that like 4 times, or?
Don't. How can I think of this? When you use the ideal gas law,
Yeah.
you just use the ideal gas law. You didn't modify the ideal gas law.
Yeah.
When you use these expressions, you just use these expressions. You don't modify them.
So then the 2s is.
So what do you put in for the wave function? Don't modify anything.
Okay.
They give it to you. And they even, do you add an additional little n to normalize it?
Yeah.
They already put it in there,
Yeah.
right? So don't modify it. Write your wave function twice. Put in what d tau is.
So then
Okay.
when it says the 2s orbital of a hydrogen atom is totally irrelevant. Like,
Yeah. Because you don't modify things. You get, and that's how important it is to know these starting points, because they tell you exactly what to do. And don't do anything extra. Okay. Now, I'm not even going to read. Whoa, why is that doing? Don't even read the rest of this question. You should know what the expression is for this, because you did projections, and you had to draw that arrow.
Yeah.
What is it?
That's not the L.
Square root of
Square root of.
C
Now,
L plus
now
I.
I don't like to use the L, because sometimes they could be talking about spin or something.
J.
So you should really use J, because there's more than one type of angular momentum here.
I have a question.
So what was this expression? What's the magnitude? Square root of
Square root of
J times.
J plus 1 times H bar.
There you go.
But
Okay.
my question is, so angular momentum equals J plus the square root of, I'm sorry, angular momentum equals all of that, right?
Now,
What is J?
where they are being a little short on their description is I really like the word magnitude, but
I guess
a lot of times we don't use it, because like if you're saying we're driving 30 miles an hour down the road, we don't say we're driving a magnitude of 30 miles an hour down the road. We just say the word 30 miles an hour driving down the road. Same thing here. They're just saying orbital angular momentum. They're really referring to what's the magnitude of the orbital angular momentum. That is what this expression is, Brad.
So even though J or L equals angular momentum, what that equation,
Different types of angular momentum.
What that equation is asking for then is the magnitude of angular momentum.
Mm-hmm.
Because I thought J or L, different types, was the magnitude. Like,
No, this expression is how you get magnitude, right? And why can you only have certain angular momenta? Because things are quantized. So you can't take any angular momenta you want. So there's only certain L values. So that's why you have to play the game this way.
So Dr. Smith, the answer for B and C should be the same.
What is this idea of? Now we haven't finished this question yet, though. What about this whole angular and radial nodes? What's this talking about?
That's like the n minus L minus 1 thing, and the L minus 1.
Okay, yeah, okay.
I don't know.
Number of angular nodes was what? Do you remember this?
n minus 1.
That's the total number of nodes.
Oh.
Total number of nodes was n minus 1.
Oh, then angular was
Angular was
L
little.
minus 1.
Stop. Little l.
Wait, angular is little L?
Angular nodes was little l.
Radial was n minus L minus
right? So I just kind of think of it this way. I just remember L, well, let's just do here. Angular is little l. And then the total is n minus 1. So I memorize the least things possible. So if you want to get the radial, right, I guess you're right. It'd be n minus 1 minus l. But I just think of the total as n minus 1. Angular is little l. Okay. Okay. Oh, we're out of time.
Sorry, Pablo. What? I was disappointed because we didn't get to those other ones. But which of the following transition? Oh, okay, that's gonna be an easy one. How many electrons can occupy the following? Okay, that's not gonna be bad either. We can figure those out.
Yeah. All right, so.
Chem.